So we will discuss with how the semi-supervised learning works. So there are some assumptions in semi-supervised learning. For example, that is smoothness assumption and cluster assumption. That means the similar data points should have similar labels. So this is known as smoothing. And the cluster assumption means the data point tend to form clusters, and points of the same clusters are likely share the same label. Okay. So, and there is manifold assumption, that is high dimensional data lies on lower dimensional manifolds, making it possible to generalize for fewer labeled samples. Okay. So the general workflow of SSL is train a model using the labeled data. Use the trained model to predict the labels of untrained model data. Select high confident predictions and add them to the training set. Retrain the model, that means once you are added labeled data, okay, then retrain again with both real and pseudo labeled data. Repeat the process iteratively. So this is how is the general workflow of SSL. So where we can use semi-supervised? Self-training. A model is trained on the labeled data. It predicts the label of unlabeled data. High confidence prediction are added to the labeled data for retraining. So that means it iteratively improves the performance. Example, a spam classifier trained on 1000 labels. Labeled email can label 10,000 unlabeled email, reinforcing its learning. And co-training, that means we can create two models. Okay, true models are trained on different subsets of feature. Each model labels some unlabeled data for the other. This mutual reinforcement improves the learning. Example, a web page classification model could use both text, context and the hyperlinks as independent feature set of co-training. That means you can have your training on the same object, but some features are given to some other system, and some set of features are given to some other system or model. Okay, so we can perform co-training. So we see that what are the advantages of semi-supervised learning? Reduces the labeling cost, improves the accuracy, and works in real world scenario. Ideal when the labeling is expensive or you have a limitation of budget and time. Applications include computer vision, image detection with limited labeled images like Google Photos, object detection in autonomous driving, self-driving cars, natural language processing, sentimental analysis, spam detection, and healthcare and medical diagnosis. So these are the application areas. We can also use the semi-supervised learning in medical imaging like MRIs, X-rays, where we have limited labeled data. Drug discovery by learning patterns in molecular structure, speech and audio recognition, text-to-speech model like Google Assistant, Siri, trained on limited speech sample, labeled speech sample, music genre classification, you can classify the music, cyber security, fraud detection, and malware detection. So using few known fraud cases and many unknown transactions. Okay, And in malware detection by learning from mix of labeled and unlabeled software files. But every goodies come with some challenges. So incorrect pseudo labeling. If the model assigns wrong labels to the unlabeled data, it can reduce the reinforcement. It can reinforce mistakes. You can create mistakes. Sensitive to data assumption. The assumptions like smoothness, that's like points will fall in like clusters, would have same label, okay, or the clustering may not hold in all cases. And computational cost, because it is computationally extensive, because whenever you find some confident in labeling the unlabeled data, then you add up and you retrain. So it is an iterative process. So for example, the graph based SSL can be computationally expensive. And I hope that we have cleared the learning paradigm or approaches, that is basically supervised and semi-supervised learnings and reinforcement learning, okay, and semi-supervised learning. Thank you goodbye for now. We'll meet in next lecture.